Well, thank you so much for the kind introduction and for the invitation. It's great to be part of this fantastic meeting. I want to start once again with Gödel's theorems. So they tell us in particular for theories like piano arithmetic that there must be statements which can neither be proved nor refuted. And I think it's quite natural to ask for examples of such statements. And in particular, we might ask for examples that come from mathematical practice, so from other fields of mathematics than logic. And there are, of course, very classical results of that in that spirit, which I will recall. And I want to present one result that has a somewhat new flavor to it in that direction today. Namely, it's an independence result that is independent, but it does not add computational strength. And I will explain what I mean by that and how that relates to previous results. So I want to start with two very classical results, just to make some conceptual remarks on them. The first result is about proving independence via the notion of computability or incomputability. And the independence statement that I want to call here is Ramsey's theorem, or rather the infinite Ramsey theorem, which says the following. So whenever you have a coloring of d element subsets of the natural numbers, so these are the subsets of the natural numbers that have exactly d elements for some number d, by c many colors. So these are the colors, and this function p is the coloring that assigns a color to each of these d element subsets. So whenever you have such a coloring, then Ramsey's theorem tells you that there must be an infinite subset x of the natural numbers such that p is constant on the d element subsets of x, or in other words, such that all the d element subsets of x receive the same color. Now, a theorem of Specker tells us that there is a computable such coloring. In fact, for colorings of pairs, say two element subsets by only two colors. And this coloring is computable, but the solution to Ramsey's theorem does not have a computable witness. So Ramsey's theorem tells us that there must be an infinite x such that the coloring is constant on the two element subsets of x. But Specker has shown that in one particular example, this x cannot be computable. And from this, we immediately get an independence result. So in reverse mathematics, there is a relatively weak, but still very interesting theory called RCA0. And this theory, RCA0, so that stands for recursive comprehension. And that theory has a model in a certain sense, which only consists of computable sets. And now, since Specker's result shows that Ramsey's theorem is not witnessed in the realm of computable sets, it immediately follows by soundness that Ramsey's theorem cannot be provable in that theory RCA0. And now, much more is known about Ramsey's theorem. In particular, there is a fantastic recent result by Pate and Yokoyama that's also a long-standing open question. But that's not the topic of my talk. So I merely want to make the conceptual point that in this case here, we can use the notion of computability to prove independence. Now, computability is mostly concerned with infinite, countably infinite, but still infinite sets. And when we have theorems about finite objects, then this type of computability theoretic argument usually doesn't apply. So let me also give you an example of this. Here we have the so-called strengthened finite Ramsey theorem. So in the strengthened finite Ramsey theorem, you color not the element subsets of the natural numbers, but of some finite set. So of some initial segment of the natural numbers for some number n, which you should think of as a very large number. So in some sense, you have an approximation to the infinite set of natural numbers. And the strengthened finite Ramsey theorem says that whenever you have fixed such a d and a number c of colors, then you can find an n, which is so large that whenever you color the d element subsets of this large set here, then you also get a large set on which the coloring is constant. So that means that the coloring is constant on the D element subsets of some set X. And now the X must be a subset of the large set that you have considered before. So now the X cannot be infinite because it's a subset of a finite set, but it's still supposed to be large. Concretely, that means two things. So first of all, you want to require that X has more than D many elements, because if X has just D elements and you consider D element subsets, then, well, there's at most one element in here. So being constant on a one element set is of course trivial. So that's in some sense a non-triviality condition. But then you want to express that this set X is really quite large. And it turns out that you can do that by saying that the number of elements of X is at least as big as the minimal element of X. So without that condition that I have now underlined, this is just the usual finite Ramsey theorem, which is not independent of piano arithmetic, for example. And if you add this condition, then you get a strengthened finite Ramsey theorem. And by the famous result of Paris and Harrington, the strengthened finite Ramsey theorem is now independent of piano arithmetic. And once again, I'm recalling this because I want to make a conceptual point. Namely, I want to show that the independence here, it's not shown by computability, but it's also shown by something that you might want to call an extensional invariant. And this extensional invariant that you use here is linked to the notion of provably total function. So I want to keep this somewhat informal, but I still want to convey an idea of what it is. So consider a computable function f from the natural numbers to the natural numbers, and consider some theory t, say a sound one. And now we say that this function f is provably total in that theory t, if the theory t proves termination for some algorithm that computes f. So f can be computed by many different computer programs maybe, but for some of them t should show that the computation terminates on each input. And now what Paris and Harrington have shown in their original paper is that any provably total function of piano arithmetic is dominated by the function that is associated with the strengthened finite Ramsey theorem. So this function takes as input numbers c and d, as in the finite Ramsey theorem, or maybe it takes the Cantor code of the pair CD if you want a unary function. And it outputs the smallest number n such that the theorem is satisfied. And that immediately gives you an algorithm to compute that function. Namely, you can simply search for that number n. So you first check whether the theorem is satisfied for n equals 0, and then you check whether it's satisfied for n equals 1, and so on until you find the correct n. And for each fixed n, you can indeed check whether the theorem is satisfied, because all these things here are finite. So you just need to look at finitely many colorings to check whether a given n works. So that's an algorithm that would compute this function here. But as Paris and Harrington showed, this function grows faster than the provably total functions of piano arithmetic. And that means that PA cannot prove that this Ramsey algorithm terminates, or in other words, Ramsey's theorem is unprovable in piano arithmetic. Okay, so now let me summarize what I've been trying to say so far. So we have seen two very classical independence results. And in both cases, independence was proved by something that you might call an extensional invariant. So I don't have a precise definition of that, and maybe some of you would think that different names would be more appropriate. But anyway, I want to call it an extensional invariant. And the two examples I gave are the notion of computability and the notion of a growth rate for a function from n to n. And one important consequence of this observation is that the two independence results that I've showed, they can be proved without invoking Gödel's theorems. So we do not reduce to consistency and infer unprovability from that, but we really use some invariant as we would do in any other area of mathematics to show that a certain situation cannot occur. Now, Hilbert's program places the focus on pi 0, 1 sentences. So these are sentences that have the form for every natural number n, some theta holds, and this theta is a bounded formula in the language of first order arithmetic. So in particular, the theta can be decided for each fixed instance of the quantifier for each n. And for these sentences, the situation is a bit different. So first of all, it seems that we do not have any extensional invariants. So nothing like computability or growth rates will work to prove independence for this type of sentences. Or in other words, all independence proofs that seem to be known or even in the air use Gödel's theorems. And also, we have very few examples of independent statements on this level of pi01 statements, except for consistency. So there are some exceptions. There's a paper by Szilard from the 80s, I think, where he gives an example. And his example is somewhat similar to Ramsey's theorem, but it's about colorings of structures in the sense of model theory. And so you could argue, well, if it's about structures, then there's some logical notion involved. So maybe it's not as natural a mathematical independence results as the ones that I showed before. And also, of course, Harvey Friedman in his talk earlier this week showed us that he is working on examples of pi01 independence, in fact, from extremely strong set theories. So that sounds like fantastic results, and I'm very, very much looking forward to them. But in any case, I think it's fair to say that this level of pi01 sentences, which are so important philosophically from the viewpoint of Hilbert's program, that on this level, we have far fewer examples than on the level of pi02 statements, where we have all these very well-known results, like Paris-Harrington, for example.
I should add that there's, in that list of things that I mentioned in my talk, along the way was one that I believe is essentially con-PA.
Okay.
Before I get into sections, it's the one that's where I just asked for order invariance over Z1 and little n.
Yes.
Yeah, and then there's of course the issue of these things are implicitly pi01.
Yes.
As the business of what's the best way to talk about the inner combinatorial structure.
Yes.
Yeah. You know, and that's a long story, and you know, to be continued. Okay, go ahead.
Thank you very much. And yeah, those are fantastic results. I really think that it's an extremely interesting question that's still, well, to some extent open, finding more examples of independent pi01 sentences. And I'm very much looking forward to these results. But for today, I want to set myself a goal that's somewhat more modest, easier to accomplish. Namely, I won't look at pi01 sentences, but I will look at sigma02 sentences. And these are sentences of the form, there is some natural number n, such that for any number n, something bounded or decidable happens. So that's a more liberal class than pi01, which means, as I said, that the aim that I'm setting myself is more modest than pi01 independence. But I think it's still very interesting because for these sigma02 sentences, 1 and 2 also apply. So as far as I can see, we don't have any extensional invariants that would cover these sigma2 sentences. And also there seem to be few mathematical independence results. So that's what I want to talk about today. Now before, okay. Now I have some second sort of introduction. Namely, I want to take another look at Genson's ordinal analysis. And we won't look at any technical details here either. But what I want to make a conceptual point once again. So what Genson showed in his ordinal analysis is that to any proof in piano arithmetic, you can associate an ordinal number or a notation for an ordinal number, O of p, which comes from this ordinal epsilon naught. So yeah, the important point for us is that epsilon naught is a well order. So to any proof, you associate an element of a well order. And Genson's assignment has the crucial property that piano arithmetic proves the following. So if P is a proof of contradiction, then there's another proof P prime of contradiction, which receives a smaller label than P from this well order. Now, seen from the outside, that statement is void, right? Because there are no proofs of contradiction in piano arithmetic. But piano arithmetic doesn't know that because it doesn't prove its own consistency. So from the viewpoint of piano arithmetic, that's a substantial statement. And now the observation that I want to make is that we can derive consistency in two ways which maybe look similar, but they're actually different. And it's precisely this difference that I will exploit in the rest of this talk. So the first way to derive the consistency of PA from Gensen's observation is to use a notion of primitive recursive well-foundedness, which says that there is no primitive recursive sequence in this well order epsilon naught that descends forever. And I can use that to derive consistency as follows. So assume there is some proof P of contradiction. Then by this observation of Gensen, we get another proof P prime of contradiction with a smaller label. But then we can apply the same observation to P prime, and we get another proof P prime prime with even smaller label. And if you continue that way, then we get an infinitely descending sequence in that well order, which is indeed primitive recursive by Gensen's construction. And so this contradicts this primitive recursive well-foundedness statement here. And if you work out the logical complexity, then you'll see that this well-foundedness statement has complexity pi02, just as these classical independence results of, for example, Harris-Harrington. The second way to conclude that PA is consistent is by a principle of transfinite induction. And that works as follows. So what you want to prove is that for each element of this well order, any proof P that receives a label below that element does not prove a contradiction. And in the induction step of your transfinite induction, you argue once again by contradiction. So you assume that P does prove a contradiction. And then by Gensen's construction, you get another proof P prime of contradiction with a smaller label. But then the induction hypothesis tells you that this P prime cannot actually be a proof of contradiction. And so you learn that P itself couldn't have been a proof of contradiction either, and that completes the induction. And now if you look at that very closely, then you will see that this is induction over a pi01 formula. Namely, the pi01 formula states for any P, if the label of P has the correct size, then P is not a proof of contradiction. So it's for any P, so it's pi01. And crucially, this pi01 formula, it doesn't have parameters. And that's because you quantify over the proofs. So in this case, one of the descending sequences, in a sense, the assumed proof of contradiction that you start with to construct your descending sequence, that acts as a parameter. But in the second case, you quantify over that proof. So the statement doesn't have parameters anymore. And that's important because if it doesn't have parameters, then you don't need to take a universal closure. And if you now look at the logical complexity, then you will see that this is sigma 02. And that's precisely the complexity of the new consistency, of the new independence phenomenon that I want to look at here. So in the rest of this talk, I will briefly discuss some classical work related to this first approach here. And then I'll present some new results related to the second one. But before I do that, I want to briefly ask the following question. Why is it the case that there is quite a lot of classical work on approach 1, while at the same time approach P has, I think, not been considered to the same extent? And I think there are several reasons for this. And I want to give one. Namely, my argument is that this first approach, which uses well-foundedness rather than transfinite induction, has maybe been preferred by some authors that are associated with a finitist standpoint. So one author that I want to cite here is Takeuchi, And I have two quotations from his book on proof theory. So first of all, he says that the proof of consistency of, for example, piano arithmetic relies on the following type of principle. Whenever a concrete method of constructing decreasing sequences of ordinals is given, any such decreasing sequence must be finite. So that's precisely this concrete method you can maybe translate as primitive recursive. So that's precisely this type of primitive recursive well-foundedness statement that we saw before. And now the second quotation, here it seems that Takeuchi does indeed link this principle to some extent to the finitist standpoint. Namely, he gives a proof of primitive recursive well-foundedness for this well-order epsilon naught. And with respect to that proof, he says the following. He says, our standpoint is like Hilbert's in the sense that both standpoints involve Gedankenexperimente, so thought experiments, only on clearly defined operations applied to some concretely given figures. So I would interpret that as saying that this proof of well-foundedness, primitive recursive well-foundedness that he gives, is indeed well aligned with the finitist standpoint that's associated with Hilbert. And in that connection, I also want to briefly mention Hilbert's view on universal and existential quantifiers. So the two quotations that I have here are quite well known, I guess, but I want to show them anyway. So Hilbert says that a universal statement can be seen as a hypothetical judgment that comes to assert something when a numeral is given. So the idea is a universal statement should probably be thought of as a pi01 statement here. And a pi01 statement cannot be decided. So in that sense, it's not a fully meaningful statement in the sense of finitism, but at least whenever you plug in a concrete numeral for the universal quantifier, you get a decided statement which is thus acceptable from the finitist standpoint. So universal statements or pi01 statements, they are not fully meaningful, maybe not first-class citizens in the sense of finitism, but they are still some sort of judgments. I mean, at least they are hypothetical judgments, and that's certainly much more than being completely non-meaningful. On the other hand, existential statements seem to be more problematic. So Hilbert says at some point that well, the existential quantifier is problematic because one cannot, after all, try out all numbers. Or in other words, existential statements that they cannot be falsified. And I don't want to make this too strong, but I think one can argue that this means that sigma 02 statements are maybe less finitist, less meaningful finitistically than pi 02 statements. And my reasoning here is that from this first quotation, that would suggest that pi 02 statements, they can be seen as something like hypothetical sigma 01 statements. And then sigma 01 statements, okay, they do contain an existential quantifier, so they are somewhat problematic, but they are still semi-decidable. And we have Markov's principle, so there is some computational interpretation there. On the other hand, if you have a sigma 02 statement, you cannot read that as a hypothetical judgment at all, because the existential quantifier is at the outside, and you really can't reduce that in complexity. You can't decide it. So yeah, maybe that's less finitistically meaningful. But I'm going to speak about sigma 02 statements, and I still think that they are very interesting for several reasons. So one reason is that they are important in mathematics. So for example, finiteness statements will often be sigma 02. And also, as we shall see, these sigma 02 statements have very interesting mathematical properties as well. Okay, so I promised that I would show you the classical situation for pi 02 statements. So here it is. It's an equivalence between several assertions over piano arithmetic. In fact, it holds over much weaker theories such as primitive recursive arithmetic as well. The first of these equivalent statements is the primitive recursive well-foundedness of epsilon 0 in terms of descending sequences, as we saw before. And now, as I mentioned, from Gansen's ordinal analysis, you can see that this first statement here implies the consistency of PA. But actually, if you look at it more carefully, then you will see that it yields more than consistency. Namely, what it actually yields is a principle known as uniform pi02 reflection. So that's the statement that says for every number n, if PA proves the nth instance of phi, then this instance is actually true. And here phi ranges over pi02 formulas. And now the classical result by Paris and Harrington also not only shows that their principle, the strength and finite Ramsey theorem, is independent of PA, but it shows that this theorem is actually equivalent to uniform pi02 reflection. And what I want to do in the following is present a completely analogous result on the level of sigma 2 rather than pi 2 statements. So instead of primitive recursive well-foundedness, we will have this principle of parameter-free pi1 induction. And here we will also have some reflection statement. And here the aim will be to get something that is as close as possible to mathematical practice. So the first thing I want to do is show you this statement of mathematical practice that I'm hoping to put in the place of the third statement. And this is related to Kruskal's theorem. So I want to mention that, of course, there's a very famous independence result associated with Kruskal's theorem due to Harvey-Friedman. And that's also pi01. And I will use, well, very similar technical arguments, but I will give a formulation of Kruskal's theorem that's sigma02. So Kruskal's theorem is about finite trees. And for simplicity, I want to consider binary trees only. And I also want to assume that the left and right successor of each node in the tree can be distinguished. So here you have a tree, for example, and well, this here is marked as the left successor of that node, and that one is marked as the right successor. The results remain true if you cannot distinguish left and right successor, but that's quite a bit more difficult. So that has been shown by Andreas Weiermann together with a student, I believe. Anyway, I want to consider these type of trees. And for such trees, S and T, I will write S is smaller than T if there is an embedding of the tree S into that tree T here, and this embedding has to preserve infima in the tree. So what that means is, for example, this node here is the infimum of two other nodes, because it's the largest node that is below both of them. And so if you look at the images of these two nodes, then that infimum should also be mapped to the infimum of these in the other tree, which is this node here. And maybe the example is not ideal here, so let me extend it a bit. Let's say we have another root node here. And now the point is that it's not allowed to send this root here to that one. So that would not be a valid embedding because, this node is the infimum of those two. So it has to be sent to the infimum here, which is this one and not that one. Okay, so I mean, I won't show the proofs to such an extent that this will actually come up again, but I still want to mention it. Now, what Kruskal's theorem says is that if you have any infinite sequence of such trees, then one tree in the sequence can be embedded into a later one. So there are indices I smaller than j such that the earlier tree ti in the sequence can be embedded into the later one. And as I mentioned, the theorem remains valid for trees that are not binary, but it becomes much stronger. So I'm considering the binary version here because it is connected to piano arithmetic. Okay. And now it's well known that Kruskal's theorem, or more generally statements about well partial orders, they can be reformulated in a different way, namely via a finite basis property. And I want to state that finite basis property directly in the setting of first order arithmetic. So the finite basis property says something like any infinite set of trees has a finite basis. And in first order arithmetic, I want to consider definable infinite sets. So these sets will be given by some formula phi. And now by k phi, so k stands for Kruskal, I want to denote the following finite basis property. So this property says that the set that is defined by phi has a finite basis A. And the fact that A is a finite basis means the following. So first of all the elements of that finite basis should belong to the set defined by phi. And on the other hand, if I have any element of this infinite set potentially defined by phi, then there will be some element S of my finite basis A such that this S embeds into the given element of my infinite set. And now I claim that all these instances are true. So this is a corollary of Kruskal's theorem. And in fact, if I wouldn't just consider arithmetically definable sets, but arbitrary sets, then that would be equivalent to Kruskal's theorem. Okay, so let's check that these instances are true. I claim that otherwise, I could construct an infinite sequence of trees that contradicts Kruskal's theorem. So Ti does not embed into the later tree Tj whenever I is smaller than j. And in order to so construct such a sequence by recursion, and in order to make the recursion go through, I want to demand an additional property, namely all the trees in this sequence, they should have property phi, i.e. belong to the infinite set that is defined by phi. So for the recursive construction, assume that we have already constructed the trees up to Tn-1, and now we want to find the next tree Tn. And the idea is simply, so we want to prove this, this finite basis property. So aiming at a contradiction, assume that it's false. But if it's false, then this finite set that we have already constructed cannot be a finite basis. So this formula here must fail. And if it fails, then one of the conjuncts must fail. So the first possibility would be that the finite set that we have constructed so far contains some element that does not satisfy phi. But that contradicts the side condition. So the side condition is that I only add trees which have this property phi. So that here will be true. So that means that the second conjunct must fail. But if the second conjunct fails, then this means that there is some tree T such that it has this property phi, and also for all elements of A, so for everything that I have constructed previously, this thing does not embed into T, and then I can simply take that T here as my next Tn. Okay, so these instances K phi are true. And now I can finally state the axiom scheme, or the independence principle that I have promised. So the independence principle that I have promised is in fact not a single statement, but an axiom scheme. And I will discuss that point a bit more later. And this is the axiom scheme here that I want to prove to be independent of PA. So this axiom scheme consists of all these finite basis assertions, where the infinite set is defined by a sigma 0,1 formula that doesn't have further free variables. So the formula has one free variable because it's supposed to define an infinite set, but it doesn't have any parameters. Okay, and maybe to state that, because there are maybe too many symbols in this line, maybe just to say a bit more intuitively what it means that any sigma 0,1 definable, so any recursively enumerable set of these binary trees has a finite basis. And maybe at that point, I could also mention briefly why I think this restriction of Kruskal's theorem, this particular axiom scheme, is reasonably natural from the viewpoint of mathematical practice. Namely, one very important application of this finite basis property is in computer science. You can use this finite basis property to show that certain problems can be solved in polynomial time. This becomes more interesting if you consider the graph-minor theorem rather than Kruskal's theorem, because there are more computational problems associated with arbitrary graphs rather than trees. But conceptually, it's kind of the same situation. So the finite basis property can be used to establish decidability in polynomial time. And often when you show that something can be decided in polynomial time, you will already know that it is decidable by some Turing machine. But if it is decidable, then it can certainly be expressed by a sigma 0, 1 formula. And that means that this axiom scheme here is enough for many applications of Pascal's theorem in computer science. So I think that makes it natural to some extent. Okay, so this axiom scheme is the new independence principle that I've promised. And I want to show two things about it. First of all, that it is actually independent. That will be shown on the next slide. And secondly, and this will be shown here, that it does not add computational strength, or that it does not add provably total functions. And that's what, in my view, makes it interesting and distinguishes it from the classical independence results that I've shown before. So the claim here is that piano arithmetic without the axiom scheme has the same provably total functions as piano arithmetic together with this axiom scheme. Okay. Now, the whole point is that the instances of this axiom scheme, they are true sigma 2 formulas. And at that point, this restriction here, no further free variables, is crucial. If you allow free variables here, then you have to take the universal closure of the axioms, and then you get pi3 formulas. So you uniformize in a certain way. But if you don't admit free variables, then you can check that these are sigma 2 formulas. So they're of the form exists for all. But now, if such a formula is of the form exists for all, and if it's true, then it will be true for some witness of the existential quantifier. So pick that witness, and what you then get is, so if you fix a witness, the existential quantifier will drop away. So now you get a pi 0, 1 formula, which implies this instance here. So for the purpose of this proposition, adding this axiom scheme with instances of complexity sigma 2 is the same as adding axioms of complexity pi 1. And it's a well-known result that adding axioms of complexity pi 1 doesn't add provably total functions, but I want to recall it as well, because I think it's a nice argument. So assume that f is some function, some computable function, such that totality can be proved in PA plus the axiom scheme for some algorithm that computes f. And now I will show that for a different algorithm that computes f as well, totality can already be proved in PA without the axiom scheme. And that works as follows. So as I just explained, these additional axioms here, they can be replaced by a pi 1 statement for all n theta of n. So we can assume that it is this statement that is used in the proof of totality for the given algorithm that computes f. And now the new algorithm that computes f, it does the following. So it does two things in parallel. First of all, it runs the algorithm that we are given. And if the algorithm turns out to terminate, then it outputs the result that this algorithm dictates. So it outputs the value of f. And at the same time, we search for a number n such that, which is a counter witness to this statement, so that not theta of n holds. And well, if we should find such an n, then we just stop the computation and we say that the algorithm outputs 0 as a default value. Now, from the outside, we know that these axioms are true. So the original algorithm will actually terminate, and there's no such counterexample. And it's really just the same algorithm. But it's not the same algorithm, but it computes the same function f. That's the point, seen from the outside. And now, if we have PA alone without the axiom scheme, then we don't know that. But what we do know is that one of the following two things must happen. So either this universal formula here is true, but if it's true, then we are actually in the extension of PA, and then we know that the original algorithm terminates, so the new algorithm will terminate by that first part. And the other case is that this universal statement is false. But if it's false, then there's a counter witness, and so the new algorithm will terminate by that second point. Okay, so that shows that adding this axiom scheme doesn't increase the computational strength of piano arithmetic. And now, the second thing I want to show is that the axiom scheme does actually yield a proper extension of piano arithmetic. I have put the names of Dick de Jong and Harvey Friedman here because, as I mentioned before, on a technical level, this is very similar to things that have been done before. But I think in this form, I haven't seen the result elsewhere. So the claim is that piano arithmetic does not prove all instances of this axiom scheme. Okay, so what Gensen did is he derived the consistency of piano arithmetic from a parameter-free pi1 induction up to this ordinal epsilon 0. And now, transfinite induction, if you look at the contrapositive, then it's a least element principle. So it tells you if there's a counterexample to the induction statement, then there's a least one. And this least element form of induction is actually very close to this finite basis property. And in order to really make the connection, what you turn out to need is a function f that maps the elements of this well-ordered epsilon naught to these binary trees. And you need that this function is order reflecting. So if the values of f satisfy this tree embeddability relation, then the arguments should be in that usual relation of ordinal comparability. And in fact, it's very easy to write down this function f here. So below epsilon 0, you first of all have the argument 0. And to this argument, you simply assign the tree that consists of a root node and nothing else. And then any other ordinal below epsilon 0 can be written in this form here, where alpha is the largest exponent in the counternormal form of the argument. And now by recursion, you can assume that you already have a tree associated with alpha, and that you already have a tree associated with beta. And then the tree that you assign to this sum here, you simply add a new root and connect it to these two given trees. So if you can distinguish left and right subtree, this really works and it's simple. And if you cannot distinguish left and right subtree, then it becomes considerably more complicated, even though it's still true. Okay, and using this function f, you can make the connection between transfinite induction and this new axiom scheme related to the finite basis formulation of Kruskal's theorem. And now just to summarize the structure of the argument once again, so we want to show piano arithmetic doesn't prove this axiom scheme by the construction that we have seen here. This axiom scheme implies transfinite induction, and Gensen has shown that transfinite induction implies consistency, but PA cannot prove its own consistency, so it cannot prove that axiom scheme. Now, there's one other thing that I want to say at this point, namely, if piano arithmetic does not prove all instances of the axiom scheme, then of course there is one instance, a particular instance that it does not prove. So why have I formulated the independence result in terms of an axiom scheme? The point is, I think that the axiom scheme as a whole is natural, but I don't see a reason why the particular instance that is unprovable is natural in itself. So the particular instance is well related to the induction formula from Gensen's proof of consistency, and yeah, I don't see why this in itself would be a sort of natural result of mathematical practice, while the axiom scheme as a whole seems to me to be a fair representation of Kruskal's theorem in first order arithmetic. So that's the reason why I'm looking at the scheme. Okay, and now I can show you the promised analog of this classical result about pi2 statements from before. So the following schemes now are equivalent over piano arithmetic. And by that, I mean that if you add any scheme any of these schemes to piano arithmetic, then you get the same theory as when you add any other of the schemes. So the first of the schemes is, as was mentioned before, parameter-free pi1 induction up to epsilon naught. Maybe as another side note, it is known that this pi1 induction is actually equivalent to bounded or delta zero induction. But that's just a side note. So the first of these equivalent schemes is parameter-free pi1 induction up to epsilon zero. And then I promised that this is equivalent to a reflection principle, and that follows from known results. Yeah, it follows from some results in the classical paper by Kreisler and Levy. If you look more closely at logical complexity and the role of parameters, it also follows from results, for example, that have been shown by Lev Miklemyshev by his ordinal analysis. So the equivalence between these first two things is really known. Okay, so the second thing is, as I said, a reflection principle. It's local sigma-2 reflection, and local means that no parameters are allowed. So that's the assertion for each sentence phi of complexity sigma-2. If PA proves that sentence, then that sentence is actually true. And now the mathematical axiom scheme that is equivalent to these other schemes is this scheme kappa sigma 1 minus. And once again, on a somewhat more intuitive level, the scheme asserts that each computably enumerable property of binary trees has a finite basis, which is a restricted version of Kruskal theorem and can be used to prove the termination of the algorithms in computer science. Good. So, okay. So ultimately, I mean, I would be most interested in having examples of pi1 independence, not of sigma-2 independence, right? So next thing I want to ask is what can we say about about pi1 statements in that context? So first of all, we can ask which pi1 sentences does this extension of PA by our new axiom scheme prove? And once you have the connection with local reflection, it's a pretty immediate consequence of Goryachev's theorem that PA together with this new axiom scheme proves the same pi1 sentences as the extension of PA by finite iterations of consistency. So Goryachev's theorem says that this holds when you replace this by the axiom scheme of local reflection for formulas of arbitrary complexity. And just by checking the easy direction of Goryachev's result, you see that you can also restrict to just sigma-2 reflection. And then on the previous slide, you've seen that that's actually the same as our new axiom scheme. Okay. And then, as I have said before, each instance of this new axiom scheme is sigma-2. And since the instances are true sigma-2 statements, they follow from two pi1 statements. So you can ask, well, can I maybe replace them? So can I maybe replace the sigma-2 statements in my axiom scheme by pi1 statements, by the pi1 statements that I'm actually interested in? But the following corollary tells us that in a rather strong sense, we cannot. Namely, there is no computable consistent pi1 extension of piano arithmetic that proves all instances of the new axiom scheme. And that's essentially a result of Kreisler and Levy. So what they showed is that if you put local sigma-2 reflection here, then that's precisely the statement of their result. And once again, that reflection principle is equivalent to our new axiom scheme. So no, there's no axiom scheme of pi1 statements that would sort of replace that, because if it would be an axiom scheme, then at least it should yield a computable extension. Of course, it should be consistent, but then it cannot contain the axiom scheme that we have given. Okay, and then finally, I want to show one other way to maybe push this down from sigma-2 statements to pi1 statements. And this is connected with adding rules. So the original independence results, they were for single statements. And I have already been a bit more liberal than that by admitting axiom schemes. And now you could be even more liberal and say, okay, instead of an axiom scheme, I want to add a rule to my theory. And there's a very nice result by Lev-Beklemyshev here, which shows that this theory here, so extension of PA, once again by finite iterations of consistency. And the point here is that this is a pi1 extension of Peano arithmetic, right? So this proves the same theorems as the extension of Peano arithmetic by the rule version of transfinite induction for pi1 formulas up to epsilon naught. So adding the rule means that you don't have the implication from the premise to the conclusion as an axiom, but whenever you have given a proof of the premise without free assumptions, then you are allowed to conclude the result of transfinite induction. Okay. So in other words, if you think it's okay to consider rules as sort of a manifestation of the independence phenomenon, and if you view transfinite induction up to epsilon naught as a reasonably mathematical principle, then this result of Beklemyshev does actually give you some sort of independence result on the level of pi1 formulas. Okay, so to conclude, let me make some questions explicit. So first of all, you can of course ask how convincing are schemes and rules really as independence results. So classically, and I guess that's really what we want the independence of one single statement, not of an axiom scheme. But it's still an interesting phenomenon, I think. And one other question that I would like to ask is, can we find a version of this transfinite induction rule that looks somehow more mathematical? Maybe one related to Kruskal-Walker's theorem. And so far I couldn't. So the finite basis version of Kruskal-Walker's theorem that I showed you is an implication. And of course I can state that implication as a rule. But the problem is that the conclusion of this finite basis statement is an existential statement. It says there is a finite basis. So the conclusion of the rule would not be universal in that case, but existential. And I think that the rule version that I was looking at was actually still equivalent to local sigma 2 reflection. So I didn't find a convincing way to formulate Kruskal-Walker's theorem as a rule that would have the same property as this transfinite induction rule considered by Lev-Beklemyshev. Okay, so let me just summarize what we did. So I gave a proper extension of Peano arithmetic by an axiom scheme, which I think is reasonably natural because it's related to Kruskal-Walker's theorem and covers applications to computer science. The instances of this axiom scheme are sigma 2 sentences, and that means they do not add computational strength in the sense of provably total functions, and we don't really seem to have any extensional invariants that would cover these statements. So the only known independence proof for this axiom scheme reduces to Gödel's theorem. And I would like to argue that this scheme kind of complements classical results on pi02 independence. So in particular, I want to point out that these results on pi2 independence, they do not have these properties mentioned here. So on the level of pi2, we really do have provably total functions as an extensional invariant, and we don't need Gödel's theorem to prove independence. So yeah, as I said, the classical results are nicer in a sense, in particular because they are about individual statements rather than schemes. But I think this scheme also adds a nice part of the picture because it has some interesting mathematical properties. Yeah, and then finally, let me just mention that there's a paper where you can find details about all this. So this will appear in the review of symbolic logic, but it's also available on the archive. And of course, if you just Google my name, then you'll also find it linked from my webpage. So thank you very much for your attention.